Hello, everyone. I'm here to present optimizing and building UI for AAA games. So let's start with a quick introduction.
Hi, I'm Carey from the code team at Rocksteady Studios in London. Today, I'm going to talk to you about some of the techniques we've used to optimize UMG. Pushing for high quality visuals is a must for a studio like Rocksteady, and we always do everything we can to squeeze every bit of performance out of the hardware we use. I'm going to share with you some of the ways we've optimized our UI, and then I'll talk to you about some advanced techniques to create AAA quality effects.
So this is Rocksteady. Here are the amazing people I work with. I'm sure you can't spot me in this picture. Let me point myself out. This is me, right at the back. But today, let's talk about one of my favorite people. So let me introduce you to Dennis. So Dennis is the engine lead at Rocksteady. Now Dennis has decided that optimizing our frame is his top priority. So our frame is way over our current frame budget. So he has a lot to optimize. So he starts looking at the obvious areas. So he's looking at actor ticks, component ticks, physics, AI, game code. But wait, UI? UI is taking 8 milliseconds per frame. UI is only some boxes on the screen, right? Right? Why is UI so expensive? So, what are we going to tell Dennis? Why is UI such a performance headache? So actually, this is a problem that exists in every UI framework I've used. So the problem is that your game wants specific UI, but UI frameworks give you a generalized toolkit. UI has ticking timelines. It has lots of interdependent layout rules. Each widget has lots of layers, and each layer applies geometry rules to the layers below. This is all made worse by the fact that people now expect UI to be quickly iterated without creating programmer bottlenecks. And UI requirements often come very late in the design process. Just think, if your game designers and UI artists handed you a perfect specification and previs of your game's final UI, then you could hand code a super performant custom solution and then ship your game. Unfortunately, game development doesn't work like that. Just as coders don't produce bug-free code first time, designers and artists have to iterate and refine their work. UI also contains dynamic text, which can lead to complex layout rules. So in the end, UI frameworks need to give a large toolkit of widgets with lots of customization options, all of which need to be authored in WYSIWYG tools by UI artists. So let's have a look at Dennis's frame. Here is the profile of a single Unreal frame. This is generally what a normal profile capture looks like for a single frame. Let's take a look at the parts of the frame responsible for UI. The parts that we are interested in are a HUD tick, slate prepass, and draw window. Okay, let's take a look at each of these parts in detail. Okay, so let's take a look at a HUD tick. So a HUD is the HUD actor and ticks like any normal actor. Here you do common HUD work, and normally here is where you typically talk to the game code and do things like creating or removing widgets. You sometimes move widgets that move with your geometry. So one function to look out for is create widget. Creating new widgets can be really expensive. And one way to avoid this is to create a pooling system. So we repeatedly call on create widgets at startup to fill these pools. So then at runtime, we just request and recycle pooled widgets. Let's move on to the draw window part of our profile. So draw window is called recursively and calls each widget's paint method. This paint method internally calls the widget's blueprint and native tick methods. And this function rebuilds the hit test grid. So the hit test grid is a quad tree for doing hit testing and widget navigation. Paint finally adds render information to the select element batcher. So one optimization approach that we took is to flatten the widget tree. Remember that the paint function calls into each container recursively. This means that putting containers within containers within containers means that you have more recursive function calls. This means more code to execute, but it also means more vtable lookups and could cause CPU cache misses. You can therefore optimize this by flattening the widget tree. It is also always worth remembering that the widget tree in the UMG designer is a direct representation of the task graph executed by the code processing those widgets. So this means that a smaller widget tree means fewer function calls, and a flatter widget tree means less recursion. So another improvement you can get is to use hit test invisible or self hit test invisible rather than using visible. So these are both visibility settings, and these both make the widget visible, but do not add the widget to the hit test grid. The difference between hit test invisible and self hit test invisible is that hit test invisible stops all of the widget's children from being added to the hit test grid. This one is therefore preferable if you don't need hit testing in this part of the widget tree. So in this case, I have a simple XP, shield and health bar that many games will have on their HUD. These are clearly widgets that are not supposed to be clicked by the user. They're not supposed to be selected and you can't navigate to them. So they do not need to be in the hit test grid. One further approach we took was to delete the tick function. Well, actually, certain classes of widget can still tick, but now others cannot. While deleting the tick function does not necessarily improve performance, I mean, maybe you're not doing a lot of work in your tick. What it does do is it prevents people from adding work every frame simply because it is easier. So this prevents artists and time-pressed coders from creating hidden performance killers. So going back to my health bar example, the easy way to implement that would be to query the player's health every tick. That would be the simplest way and often the way that coders choose to do those things, especially when they're prototyping. Deleting the tick ensures that people always have to use an event-driven approach or a more performant approach than querying something every tick. Okay, let's move on to the biggest part to optimize. So let's have a look at Slate pre-pass. So this section is Slate pre-pass. And this is one function that your engine coder may ask you about. They'll ask you partly because it's not obvious what it does. And they will also ask you partly because typically it has very little profiler instrumentation, which means that your engine coder will have a profile that just has a great big block of work in it, simply titled Slate Prepass. So what does it do? So the Slate Prepass function rebuilds all of the cache geometry entries for each widget. It needs to descend to the bottom of the hierarchy and then traverses all the way back up to the top again. So bear in mind that the geometry of widgets affects those both up and down the hierarchy. For example, the size of a table cell may be governed by its contents, but it's also restricted by the size of the row and the column. So each frame, this function gets the cache geometry values that are recalculated for the whole widget tree. So the first thing to do here is, when you're hiding a widget, you should use collapsed instead of hidden. This is because hidden widgets still have screen geometry and still influence the geometry of the widgets around them. So let's look again at my XP, shield and health bar. So if we consider this is a vertical box full of widgets. The XP, the shield and the health exist in a vertical box. If we're hiding the shield component, if we mark this as hidden, the hidden widget still needs to recalculate its geometry in the prepass. But if we collapse it, the collapse widget does not. Now, obviously, sometimes hidden is preferable for your screen layout. But if you don't need it to be hidden, you should choose collapsed. So also note that to calculate the geometry of a hidden widget, it will need to calculate the geometry of its children, even though none of them are rendered. Note that Slate Prepass always descends to the leafmost node. Collapsed is the only visibility setting that stops that recursion. So in this case, using collapsed will skip the whole branch of the task graph. UMG does provide you with a widget called an invalidation box. An invalidation box is a simple container widget, but it caches the layout and volatility of the tree below it. You can get some good performance gains using invalidation boxes, but these can cause issues. In some cases, invalidation boxes do not invalidate automatically. So this means that sometimes you see layout or animation bugs, which only a coder can resolve. And often I've seen artists just solve this problem simply by deleting the invalidation box, which effectively gets rid of that optimization. So I've also seen this. I've seen people accidentally leave in a call to invalidate every frame. Clearly, this is not optimal. Okay, so we've run through a number of techniques that your art teams and your UI coders can use to do some general optimization. But I want to talk now about some more extreme optimization. And then I'm going to talk about how to add some awesome stuff to your UI that UMG currently does not do out of the box. Now, we've implemented a lot of new widgets which internally implement the SMeshWidget class. This widget currently has no UMG implementation and, as far as I'm aware, is currently unused. So this gives you an interface to directly draw any 2D mesh with a corresponding material. So you can use it to directly generate buffers which are passed with a reference to a vertex and index buffer to the slate element batcher. In the render batch, you can use a buffer with a renderable instance count to render many instances of the mesh, passing that buffer to the material shader. So you can, in one buffer, render lots of instances of the mesh. So the obvious first example we use this for was a particle emitter. This is an obvious example of a widget that needs lots of instances of an object and needs to render lots of instances of an object and needs to be performant. So this particular emitter is rendering 200 particles. These are not going through normal slate drawing processes, but are instead laid out and positioned in a material on the GPU. So we added a UMG representation of this widget. So doing this, you can simply add basic particle emitter controls directly in the UMG designer. This allows your artist to easily use these without requiring a programmer. So because this is now a UMG slate widget, we can now spawn particles which can be layered into other widgets. So because these particle emitters are now simply UMG widgets, in this example shown here, these are just layered in their order in the UMG designer's widget tree, in exactly the same way you would layer text on top of an image. So particle widgets are just one use of this. You can use this tech to create lots of other complex widgets. It can be used for anything that is drawn many times on the screen. Just take a minute to think of anything in your game's HUD or UI that draws lots of similar instances of an object. So for example, this map here is a great example of a widget where you are drawing a lot of similar instances. It is also worth noting that all of the icons here could all be in one material instance, but each with a different parameter sent per entry in the instance buffer. This means that for this map, you could draw all of those icons in a single paint call. This helps you drawing anything that is dynamic, anything that moves with the world or moves with the camera that could cause repeated layout and pre-pass invalidation. So these widgets here are doing a simple and non-intrusive pre-pass. Non-intensive pre-pass. The widget's geometry is actually a small box. It's actually the green box you can see in the video. The particle rendered geometry is all handled by the GPU. So let's just compare the performance of this to normal UMG. So this widget is moving 200 animated items. So if we were to make this particle widget in standard UMG, we would have to do something with a complex pre-pass hierarchy, which has to move the UMG widgets and CPU operations, which then recursively builds the render data in the element batcher for every single particle, and will then send all of those as separate RHI render commands. using our new tech, we have a single box in prepass with no hierarchy, which directly creates render buffers and moves the particles on the GPU. So here's a quick comparison of a UMG widget compared to one of our particle widgets. As I mentioned before, the example is moving 200 items without pre-passes, with one paint call, with one item in the slate render batch, and transform and layout on the GPU. And remember, this tech does not need to be used just for particle systems. This can be used for any number of complex widgets. Anything where you are rendering multiple instances of the same thing, or anything where you are moving something around continuously. So why don't we just use this for everything? So with a solution like this, there is obviously a drawback. This new system creates handcrafted custom widgets for your game. We're now in the realm of creating specialized widgets. This is no longer a generalized solution. So you have to plan out which items you have that may benefit from this work. This will affect your artist's workflows. Your animations and effects now have to be done in material shaders. Your artist cannot use the sequencer tools. This means that artists may rely on coders to change these bespoke widgets, which can cause a bottleneck in your development process and can massively slow down your iteration time. But with this approach, you can build awesome tools. But that time needs to be planned. So in summary, what do we know about UI? So UI is always more performance intensive than people think. UMG is a really powerful tool. But to be this powerful, it has to be a generalized solution to your own specific problems. You can use the techniques described here to get small performance improvements or large performance gains. You can create new widgets for specialized performance critical UI. You can make UI that looks awesome and fits with your aggressive frame budget. So, in summary, you can make Dennis happy. So we've dramatically improved our UI performance, and we've done it without compromising on quality. So now Dennis just has the rest of the frame to worry about. So I hope that everybody has learned something useful. At Rocksteady, we are always looking for amazing people. So please check out our website if you want to find out more. And thank you all for listening.